So hello, I'm Ruggero Valli and I'm a PhD student at the Max Planck Institute for Astrophysics. So I wanted to start from a very familiar picture. So we have a binary that is undergoing mass transfer. And as we all know, sometimes this is not a conservative process. And so this binary is going to lose some mass and some angular momentum. And one of the crucial questions to understand this kind of phenomena is understanding how much mass is lost and how much angular momentum is lost, and how is this happening. So what kind of in what way this mass is lost. So is it from fast winds or from outflows? So imagining that we agree on a way to lose this mass, in this case, I'm picturing like an outflow, something like that. So the next question is, do the ejecta coming from this system, do they escape to infinity? Are they fast enough to escape to infinity, or do they stay bound to the system? And the answer depends really on the details on how this outflow is produced. For instance, imagine that the outflow comes from the L2 Lagrangian point. In that case, we know that depending on the mass ratio, you could have the ejecta going out and escaping very fast, or staying around and being bound to the system. And in this second case, if the material doesn't escape, it can remain around for a long time, and it has a chance to form a circumbinary disk. So what is a circumbinary disk, and how does it differ from just the outflow in the previous picture? So in a circumbinary disk, the material goes around in quasi-Keplerian orbits, and it would just keep going around in the way if it was not for viscosity. So it's viscosity that causes the material to have a very slow outwards outflow. And so this means that the tangential velocity is much higher than the radial outflowing velocity. And so this material can stay around for a while, and this means that it can also develop, it can keep exchanging angular momentum with the binary for a long time, and it can develop resonances or things like that. And so it's not just a matter of understanding how much angular momentum is lost at the beginning. You also have to keep into account what happens while the disk interacts with the binary. So this is a decretion disk in which mass comes from inside and goes outside and is outflowing outside. But you can have also the opposite process. For instance, at the end of mass transfer, some of the mass that was in the disk might try to be reaccreted in it. And I'm going to talk about accretion disks also, because they are they're the thing that I worked on, but they are also something that you find in a lot of different situations in astrophysics. You find them from star formation to supermassive black hole binaries, and of course also in post-interaction binaries. For instance, post-AGB stars, we see disks, maybe post-common envelope systems. And let's talk about what is the orbital evolution of a binary inside an accretion disk. This is just to illustrate how complicated it can be to model these things. So forget for a second about stars and stellar evolution. Imagine you just have these two objects and they are a binary, and there is an accretion disk that is accreting onto them. And we want to know how the effect of the disk will influence the orbit. So one simple question that we can ask is, for instance, does the orbit shrink or widen? And the answer depends on several effects. So we have some gravitational torque. So the mass of the disk will exert a torque on the binary. And we also have accretion torque, so that when the mass finally hits the star, is carrying some angular momentum. And finally, we're also accreting, and so changing the mass of the binary, and therefore this will also change the orbit. So in the end, if you sum up all these contributions, the net effect can be small. And whether the binary will shrink or widen really depends on the parameters of the system that you're looking at, for instance, eccentricity and mass ratio. And to make this even more complicated, these parameters change as the system evolves. So imagine this is our parameter space, and some regions are red widening, and some blue regions are for a system that shrink. And this curve could be an example of a system moving in this parameter space and going from widening to shrinking and vice versa. And if you really want to understand what happens to this system on a long time scale, you have to follow all this trajectory, but this is such a long time that you cannot do this with hydro simulations. Instead, what you can do with hydro simulations is taking one single point in the parameter space and computing for that point where the system wants to go. So you do a disk simulation at that point, and you say, well, this point is red, the system is widening. And so you can compute the gradients, the derivatives of the orbital parameters for each of the points. So what I did was taking the results of hydro simulations that I did not run myself, but they computed these gradients for several points in the parameter space. And then what I did was to compute smooth interpolations of these gradients. And from that, I can then finally integrate the orbital evolution of a system on a time scale that is so long that a normal hydro simulation could not be able to follow. And so let's look at how this looks in reality. I mean, in reality, in the model. So this is the parameter space of eccentricity and mass ratio, and each of these points corresponds to one hydro simulation that was run for 10,000 orbits or something like that. In this case, it's Magdalena Sivek. And so first thing is interpolating this space, and you get something like this. So as you can see already, the landscape is quite complicated. You have blue and red regions. And so next thing is now to integrate the orbit. And what we get is something like this. So each of these lines is one possible trajectory of a system. And you may notice that all these lines seem to cluster in the central band, which is an equilibrium eccentricity band. And this means that if you imagine starting with different systems in this space, there will be those tiny canoes. And so each of these ones is a different system. If you let the system evolve under the influence of the disk, you will see that they will settle on this equilibrium band after accreting about 10% of the initial mass. And if you let the system evolve even further, at some point they will eventually all go to this attractor point after accreting a substantial amount of mass. And so this was just to say that these are complicated because you have all these effects. You have resonances, you have attractors, and there is in general a very complex landscape in this parameter space. And so the question here is if some of these features could also be important for decretion disks during a stable mass transfer when you have the disk that is fed from the inside. So instead of leaving with conclusions, I will leave with some questions. The first one is, how does mass leave the system? And if it's possible that some of these ejecta don't go away, but they stay bound, so can we form a circumbinary disk during mass transfer? And the third question would be, can we learn something from the circumbinary disk community, the guys that do those amazing simulations, that can help us understand the stable mass transfer and the angular momentum loss? Thank you.
Is this working? Can you hear me? Oh. Turn it on. Oh, no? No? Okay. Okay, that was maybe my fault. There we go.
Yeah, great presentation. So you mentioned you also interpolate between different simulations. So do they assume are all the other settings the same between those simulations, or do you have to kind of think about like, oh, what if they have different settings or different integration timescales, and like how do you deal with that?
Okay, so this grid of points that I showed was referring to a suite of simulations done by the same person, Magdalena Sivek, in a paper, in a couple of papers. So they are all with the same physical assumptions. Everything is the same. I cannot do this, sorry. But the only difference is the eccentricity and mass ratio. And this is for Magdalena Sivek paper. I also did the same exercise with other two groups that have done a similar thing. And they also use the same physical assumptions. The only difference there is the code that they use, and they have pretty similar results. The only I would say major difference is what happens at very low eccentricity, because in this case you see that everything, if you start from any eccentricity, you will excite and pump the eccentricity in any case for these suites of simulations. In the other two, what happens is that circular systems are stable. This is the major difference, and it's not clear why is that at the moment.
So I was wondering if you can estimate the amount of mass in a putative circumbinary disk and compare it to the total mass of the binary, because the rate at which the disk is fed, the viscous timescale of the disk, that is the timescale on which the mass flows in. So it should be possible to make this comparison. And I wonder what kind of fraction do you get of a disk divided by binary?
You want to know the mass in the disk. Okay, for like mass transfer systems.
Yeah. So you start with a non-interacting binary, it starts interaction, it has a fraction beta of mass that is accreted. And so 1 minus beta times d1 dt is the rate at which you build your disk. And the rate at which you unbuild the disk by throwing mass either on the central binary or making it fly away. And so it should be possible to have that basically that fraction as a function of mass ratio or time as well. That would be, I think, interesting also to inform searches of these disks and to inform ourselves of, well, do we believe all of these? Like if I put a 10 to the minus 4 of the total mass in a disk, can it really screw my orbit that much? I don't know.
Yeah, well, that's a very good question. So we, for stable mass transfer systems, I'm not aware of anyone observing such a disk. Maybe because it's only in the fast phase, I have no idea. Or maybe they don't form at all. And for post-mass transfer systems, we observe those disks like in post-AGB stars. And usually the mass is very small. So we see something like 10 to the minus 2 solar masses. So in that case, according to these, you would not be able to change the orbit much. Just through reaccretion. But during a mass transfer phase, you are putting out a lot of mass. So maybe in that case, even if the mass of the disk at a single instant of time is not much, you are going to dump a lot of mass into it during the whole process.
Okay, so going back to this plot over here, let's say that you're rowing your boat in this very thin stability line that goes over there. So the point that you're saying is that after your binary has accreted a specific amount of mass, it always goes through that path over there. So you will feel comfortable by saying that we can develop like a couple of analytical prescriptions to put in population synthesis and say, hey, this binary, after it accretes this much, this the orbit will evolve this way following this line, this stability line?
Yeah, I think something like that could be done. I think the best way to do it would be not to decouple this from everything else in the binary, but just take the derivatives and use them, because you in a binary, in a population synthesis, you might have several contributions to the orbital change, right?
Yeah.
So this is one of them. You should probably take the derivative given from these and also the orbital change given from mass transfer and stellar evolution and tides and put all together. And that's definitely something that can be done.
Thanks. I wonder if a comparison with the observation of post-AGB circumbinary disk can be made, and if you've done it so far.
Yeah, so as I was telling Mathieu, the problem there is that the mass that you see in the disk is very small. And so these would not be able to create this. And also another problem is that in post-AGB stars, we see a whole different distribution of eccentricities, right? While it looks like here, everything would be clustered along the line. But actually, it's not exactly so. If you actually look at post-AGB stars, there is a paper from Oman, I think, that shows that there should be a bimodal distribution in eccentricity observationally. So some of them are clustered around, oh, maybe I have the plot here somewhere. Yes. So, come on. Okay, so this is the lower one is the observation plot from Oman, and you see a bimodal distribution, and this in theory could match the above one, which comes from the other simulations that I was mentioning before that say that circular systems are stable. And so if circular systems are stable, you expect an accumulation of system at 0 eccentricity and some accumulation at maybe 0.4 eccentricity. So I'm not sure if the observation and model really match, but it's interesting to look at those things.
All right, I think we need to move on, unfortunately. There's 3 or 4 more questions, so catch up with Ruggero afterward.
Thank you.
Thank Ruggero again, please.